So thanks for the introduction. I'm very happy to be here. That's my first talk with the Princeton University affiliation down there. So it's a first for me in many aspects. I just moved last week, so I'm a bit tired by all the unboxing. But I guess I'm very happy to be here. The topic of the talk today will be to try to give you a feeling of the cosmic history of magnetic fields from a galaxy formation perspective, and of course using computer simulations. So of course there is a lot to say about this, and I will only focus on, I would say, my personal biases on the questions. So yes, so the outline, I will very briefly introduce galaxy formation from a cosmological perspective and mostly using simulations. Then I will introduce you to what we think is the history of the magnetic fields in the universe. We describe magnetic field as an average quantity, as a universe as a whole, and of course it comes, as you will see, from galaxy formation, and then it's injected back by galactic winds. So I will first describe a recent work we did on the very first seeds, magnetic seeds in the universe, which can be explained in particular by the so-called Biermann battery. There is many other processes out there, but I will focus only on this one, which in my opinion is a more mature one. Then I will describe the second step in cosmic magnetism, which is the amplification of this very tiny seed field to the strength that we see today inside the Milky Way. And there is, as you will see, there is a huge range of orders of magnitude to cover. And this, we believe, is covered by the dynamo process, which is mediated by turbulence mostly. And then I will give you a very recent numerical experiment that we did of the formation of a Milky-Way-like galaxy in the cosmological context with magnetic fields. And you will see that it's quite challenging because of the finite numerical resolution that we have to deal with. So here down there are my collaborators. They are mostly from Zurich, and a few on the Sphinx collaboration I will introduce later. Okay, so let's start with a movie. That will be my introduction to galaxy formation. What you see here is the movie of the gas density in a cosmological simulation of galaxy formation, and that's a zoom on one particular galaxy that will become a Milky-Way-like object. And what you could see is those filamentary accretion, this cold stream feeding gas into the center of the halo, the dark matter halo, in which a disk is slowly forming. You can see these gigantic explosions, which are due to stellar feedback. And these explosions, or we call them galactic outflows, are really a key ingredient in the modern view of galaxy formation because they explain why star formation is reduced. Then, in a second step, you can see now a very large disk form. It's very quiescent. You don't see those explosions anymore, right? And so we believe that this galaxy formed with these two epochs. One very violent epoch, which is dominated by galactic outflows. Of course, a very turbulent epoch, where turbulence inside galaxies is very high. And then you have this quiescent epoch at late time, where the galaxy is actually quite quiescent with a very thin disk, and turbulence is low, right? And I want you to keep in mind these two epochs as a key, I would say, property of what we believe is the galaxy formation scenario. Of course, all this might turn completely wrong in 10 years, but that's our view of the problem today, right? Okay, so the key here is that the late time evolution, we can form those nice disks. So you see here, the two upper panels is the gas distribution. You see a very thin gas disk, a very low level of turbulence. And below, you can see the stellar light as observed by a Hubble Space Telescope-like experiment. And you see that the result is quite spectacular. But I want to stress two caveats. We are far from having a successful model here, at least in my opinion. The first caveat is that down there, you see the bulge of this galaxy is huge. And it's a very bright bulge. And we are having a hard time forming galaxies that looks like real galaxies we observe around us. And a lot of them, probably half of the disk galaxies are bulgeless. And forming bulgeless galaxies is really hard, right? And the second thing that you can see in the other image, the side-on image, is that the stellar disk is quite thick. Right? And again, this is hard to form thin stellar disks as thin as we observed. Right? This could be numerical issues. This could be also the physical modeling, which is not correct. There is many, but otherwise, so I'm giving you the caveats here, but otherwise the result is quite satisfactory. So maybe we could use those simulations to study how real galaxies form, and here we're going to study magnetic fields, right, using this methodology. Okay, so magnetic fields, the history as it is from, I would say, 50 years of research, is that initially, when the first stars are forming, and I will show you results of that in a minute, there is a process called the Biermann battery, which will create microscopic currents due to electron and ion being slightly moving at different velocities. So there is a current, and this microscopic current will create a field. So this is called the Biermann battery. It's based on electron and ion collisions. It's plasma physics. It's relatively well known and well understood. And Nick Nedin in 20 years ago performed the very first simulation of this process of the Biermann battery and showed indeed that when the first galaxy formed, you could create an almost pervasive field everywhere in the universe, volume filling, of 10 to minus 20 grams. It's tiny. And this value comes from the physics of the problem. I will come back to this later. Then, okay, let's take another point. So that's our redshift, I would say 6. So the universe is 1 billion years old. And then the cosmic ionization, I will come back to this later, create this field at 10 to minus 20 grams. Then the other point in time we have is the local interstellar medium in our galaxy, where we see that the field is 10 to minus 6 grams. So you see that there is 14 order of magnitude to explain between the universe back then, where Biermann battery was likely process to create seed fields, and then today, where we have 14th of orders of magnitude larger fields. So how can you get there? Right? 14 order of magnitude is a lot, right? So what's even more surprising is that if you look at observations of quasar line of sight, so you have very high redshift quasars, and then you can measure the magnetic field along the line of sight, and you can see this light intersecting galaxies, and we can measure the magnetic field in those intersecting galaxies. And we have measurement of the magnetic field at redshift 1, 2, 3. So even, and the surprising results is that the magnetic field is actually 10 times larger back then in those galaxies than it is today. So that's really hard, right? You have to go from 10 to minus 20 to 10 to minus 6, but actually when you go there, it's even larger, right? So you see this very, very fast increase of the magnetic field strength that you need is a problem, right? And so the traditional theory here to explain magnetic fields is based on observation of local galaxies like this one you see here, IC 342, where you see these very nice disks, exactly like the disk I've shown in the movie, and a well-ordered magnetic field. And when you look at this system and you try to think about the dynamo process that can amplify the field, you end up playing with the notion of the large-scale dynamo. So I'm not going to cover this aspect here, but that's what people were working on since the 70s. And large-scale dynamos are great because they can amplify the field, but they are slow. The fastest you can do here is to amplify the field at a rate which is equal to the rotation rate of the galaxy. So you see the Milky Way has performed 20 rotations since it exists. So 20 rotation, you get 20 e-folding time if you're lucky, and so it's hard to get a safe amplification, especially if you have to amplify the field already at very high redshift, right? Which is the challenge. Okay, so that's the picture. I would say old school picture. But what those people didn't know back then is that galaxies, especially at early time, were dominated by strong outflows. And so galaxies at high redshift, they don't look like this nice quiescent disk. They look like a mess. They look like they're exploding all over the place with projecting gas in the intergalactic medium. Then there is gas falling back in, and this maintain a very strong turbulence. And that's the new the novelty here in terms of galaxy formation. Right? So, okay, so let me briefly show you the equation we're solving, which is the ideal image equation. So that's exactly these three equations we're solving conservation of mass. I haven't shown conservation of mass, sorry. But there is the conservation of energy up there, conservation of momentum, and of course, the induction equation that describes the amplification of the magnetic field. You can see from this equation, by the way, that if B equals 0, initially, it stays 0. So you need seed fields, right? Once you have those seed fields, then you can amplify them using a dynamo process. So we performed, like 10 years ago, some very early galaxy formation simulations using ideal MHD, and the result was a disaster. And the field growth was very weak. And the reason is that in those early models, feedback was weak, was too weak. Nowadays, and that's the situation we're in, right? Now we know from other observational facts that we need those very strong outflows in galaxies. And now we are performing our simulations that have strong outflows, like those explosions I showed you before. And now I will show you that if you include these physical processes, then there is a turbulent dynamo that kicks in. So it's not a large-scale dynamo, it's more like a small-scale dynamo, which is driven by small-scale turbulence. Okay? And so that's the current model, I would say, and that's the model I want to explain and show you today. Okay, I'm sorry. So, okay, so first, the seed fields. So this is a recent paper that we worked with my students on trying to compute with, I would say, a modern view, this Biermann battery process at high redshift. So the Biermann battery process is just a non-ideal term that you add here, you see, that's here, this non-ideal term that you add to the MHD equation, the induction equation. And this ideal term comes from this current between electron and ion, which are not moving exactly at the same speed. And there is a small drift, and you can compute this drift in some stationary limit of the plasma physics here. And you see that it depends on the pressure gradient, or the electron pressure gradient, and 1 over the electron density. And that's very important, right? So you see that if the electron density and the electron pressure are proportional to each other, then this term here can be expressed as a gradient of another quantity, which is usually called pi. And then the Biermann battery is the curl of a gradient, and you know from analysis 2 that the curl of a gradient is always 0. So if the density is proportional to the pressure, there is no Biermann battery. For example, an isothermal gas, the density is proportional, and the pressure are proportional to each other, and so no Biermann battery. An isentropic gas, same thing. Right? So you see that you need misaligned pressure and density gradients in order to create these currents. Right? And so there is such an example in the early universe, which is when you have a photoionization coming from a star-forming galaxy. And you see down there a plot showing what we call the strong grain sphere. So you have here a star, you see shining in a modulated density background. So you see there is a sine modulation in the background that you can see here. And you see here the strong grain sphere, which is propagating in this density modulation. And here we have a misaligned pressure and density gradient. And you see that there is a magnetic field that comes out, which is at the level of 10 to minus 20 Gauss. And where does this 10 to minus 20 Gauss come? It comes from the physics of the Biermann battery. So you take just the scaling, the simple scaling law here, which is dimensional analysis. And you see that if you plug in the temperature of the photoionized gas, which is always set to the 4 Kelvin, if you plug in the size of the strong grain sphere and the age of the strong grain sphere, you get an estimate of the Biermann field, which is 10 to minus 20 Gauss. So it's very simple.
That must depend on the luminosity of the star that you've assumed, or?
So the luminosity of the star will give you the size of the sphere.
Right.
Yes, but not the temperature. The temperature is always 10 to the 5. Okay, right. It depends on the spectrum a little bit. Right?
No, but you're saying
the luminosity of the star will set the size of the strong grain sphere. Okay. So a bigger sphere will give you a smaller field, but the age will be also longer. The time it takes for the sphere to propagate. So the two kind of cancels out. So it mostly depends on the temperature. That's the takeaway message. Right? Of course, it depends also on the modulation, on the details of the geometry. Right? If it's perfectly symmetric, it's 0. Okay, so this test is actually quite difficult to do. And you need for that the right numerical scheme. So I'm going to spend a few minutes describing the numerical scheme we developed here. which is a scheme that preserves this property that isothermal flows have zero Biermann battery generated fields. And you see, for example, here an experiment where we have an isothermal flow, but we use the naive method that anyone would use naturally. And you see that you create a field which is at the level of the truncation errors of the numerical gradient, right? So you have it's a small error, right? But it's still there. If we use this method that I'm going to describe quickly, then there is zero field created. Right? So we basically maintain the notion that isothermal flow have zero generated field at the level of the machine round-off errors. So what is the trick here? The trick is to rewrite the previous gradient into two components. One, which is the gradient of the temperature. So if you have an isothermal flow, obviously it goes away. And then the temperature and the gradient of the logarithm of the density. And if you have an isothermal flow, then you see that the electric field is actually a constant times the gradient. And so if now you take the numerical curl of the gradient to find exactly zero. So by construction, our scheme preserves exactly this property that an isothermal flow should have no field. And you see now that actually, so these are examples of these Strongren sphere tests. And here, the two left panel are it's a very hard test. It's a Strongren sphere test with zero density modulation, meaning that you should find zero magnetic field. And you see that the naive method actually finds quite a large field here. And the better method finds a field which is much smaller, right? Of course, just to come back here, if I can, yes. You see that this is not strictly isothermal, right? The isothermal sphere, the Strongren sphere, is not strictly isothermal, right? So you don't expect zero field due to isothermality, but you expect zero field due to the geometry, which is again poorly captured by a Cartesian grid. So you see that the improvement here, when you move from the naive method to the improved method, is basically 1 to 2 orders of magnitude lower field. So it's a lot. Right? So it's clearly here a big improvement in the quality of the numerical solution. And you can see now, so those are the two right panels. Now. You can see that with 20% modulation, which is this exactly this test here that I'm showing, you see that the improved method converges to the right solution much faster. So that's the key message. While the naive method is still not converged, still fighting to converge. So this test is surprisingly difficult. Right? And actually, we realized this recently by performing those tests, that you really need to be careful with the numerical technique. Okay, so now let's move on to the results. So what we did here was to use a simulation framework that's called the Sphinx project, which simulates the epoch of ionization. So we are looking at a very tiny box. So this box here is a periodic box, which is 1 megaparsec across. Right? So 1 megaparsec is basically the size of the local group around us, right? But now that's the entire periodic box that describes our universe. So you see that's really small. But since we stopped the simulation at redshift 5, we don't really care, right? At that time, we only formed dwarf galaxies. There is no giant galaxies like the Milky-Way or the local group. They will form later. And you see, by the way, that you have in this periodic box the typical filamentary structure. And all these white circles that you see are dark matter halos, tiny dark matter halos. And now the beauty of this Sphinx approach is that thanks to this tiny box, 1 megaparsec, you can really zoom in those dwarf galaxies and resolve the interstellar medium inside those galaxies. And so that's the overall goal of the Sphinx project, is to resolve the interior structure and the turbulent interstellar medium inside the galaxy while having a relatively realistic cosmological environment. And so thanks to that, we can study the epoch of ionization, looking at how the early dwarf galaxies form star, and then shine UV light and will reionize the universe around them. Okay, so what we did, so it's a very big project with many collaborators, and we focused on the Biermann battery. We said, okay, let's run those simulations, focusing now on the Biermann battery. Okay, so what we get? So we get actually what we were expecting, which is that all these new star-forming galaxies are actually generating a field of the order of 10 to minus 20 Gauss. But actually, we get two surprises. First, we got what we were expecting, which is that we got a field around 10 to minus 20. So you have to picture the orange pervasive field here, which is, by the way, this is at the end of the simulation at redshift 6. But we also were very surprised to see that in the vacuum behind the Strontium spheres, we have also a tiny field there. Where does it come from? First surprise. And second surprise, we see this gigantic blue region that you see here are actually galactic outflows. And they also generate their own field, which is more intense actually than the photoionization of the Strontium sphere generated field. And so we went back to the literature, and we realized that almost 10 years ago, Naos and Narayan worked out the linear regime of the Biermann battery by just solving the linear equation of the cosmological perturbation theory. And because there is a very subtle thermal balance between the CMB, the gas, and a lot of different processes, you have slightly misaligned density and pressure gradient already in the linear regime. And this creates this field down there that you see in this diagram that shows the density of the gas versus the magnetic field. You see that down there at 10 to minus 25 Gauss-ish, there is this linear regime of perturbations that have this little magnetic field. Then, of course, on top of that, we have a second process, which is the photoionization from these star-forming galaxies, which create this branch here, right? At 10 to minus 20 Gauss. And of course, the denser the gas, the more compressed the field becomes. And you expect from ideal NHD, so that's the ideal NHD term, you expect this evolution here, B proportional to rho to the 2/3. Right? And then you have this second branch here, which was also a surprise, which is higher, which is due to the supernova explosion, the galactic outflows. And this second branch here is, why is it higher than the photoionization? Because the temperature of the supernova-driven galactic outflow is not 10 to the 4, it's 10 to the 6. And remember the scaling relation that I showed earlier, you can explain a higher temperature by just, you can explain a higher field, sorry, by just plugging in a higher temperature. And so that's how we explain these different processes here. There is also another process that is starting very weak, is the dynamo. There is a very weak dynamo here occurring inside those turbulent galaxies. I showed you a zoom before. Okay, so it's a lot of process going on all together, right? And that's really the startup of the cosmic magnetism here. At least if we adopt this Biermann battery process as the main process. So if you look at the time evolution of the mean field in the universe, so we have this curve here. So I want you to ignore the blue one. The blue one is what we obtain using the naive method. And so it's wrong, right? Just to show you that using a naive method changed the results because we are dominated by truncation errors. Right? Using our improved method, we converge to the right value, which is the value predicted analytically by Naos and Narayan, which is this constant field. So the field here, the mean field in the universe, is constant as a function of time. Right? That's kind of a nice result for this linear regime. Then, once the first star formed, UV light is shining, and then you have this Strontium sphere regime. Right? And here in green, you see a simulation that we perform by turning off supernova explosion. And so that's the only due to Strontium spheres, to photoionization radiation. Right? But then, once supernovae starts to explode, there is a second branch, boom, which is over there, right? The orange value. Okay, so you see linear regime, photoionization, and galactic outflows. And then here, what we did, we performed a second simulation with higher resolution. So the red one is with higher resolution, and we see that the magnetic field is not converging. The temperature is converging, but not magnetic field. And this is a sign that we have a weak dynamo. I will come back to this.
Is this a space averaged or mass averaged?
It's volume weighted.
Volume weighted. Yep.
Okay, so that's the first. So you see, we stop at redshift 6 in those simulations, right? And remember, the box size is 1 megaparsec, so it's really tiny. And there is no way we can go further because we're going to see. Usually, when you go too far in time in those simulations, you form a large cross, which is a spurious effect due to the boundary condition. Right? So we have to stop at redshift 6, otherwise it becomes. And actually, some people, experts, would already recognize a cross here forming. Right, so there is some cosmic variance here. There is a lot of caveats by using these small particles. Right? Okay, so now I think that's it. Yes, for the Biermann battery. So using this relatively complex story, right, based on the Biermann battery process, now we have a realistic scenario to generate seed fields, and you see that those seed fields. If you ignore the dynamo that is starting already, right, they go up to, the mean field go up to 10 to minus 18-ish. And if now you look at inside the simulation, you can go maybe as high as 10 to minus 15. And again, there is a little bit of a dynamo here in the densest region. So we need another process to take over. Right? And as I said, this other process is the turbulent dynamo. So to explain a little bit what's happening here, we are looking now at a numerical experiment of an isolated dwarf galaxy. Right? So instead of forming a dwarf galaxy like before in the Sphinx project, in the cosmological context, here we did something much simpler. We formed an isolated dwarf, so it's an isolated cooling halo. And if you don't, so you have cooling, you have star formation, you have all the physics you want, except on the left, you have no supernova feedback, and on the right, you have strong supernova feedback. And when I say strong supernova feedback, it's important because the way we implement supernova feedback depends on a lot of parameters. Okay, and you have to tune those parameters so that the effect is strong. Okay, I want to make this point clear. Right? This is not ab initio first principle simulation. Okay, so if you tune your parameters to have strong feedback, then what you get is instead of a nice thin disk, in case there is no feedback, so you see the disk face on and side down, we get this messy, turbulent environment. And the key point, and you see this is side on here, down there, this side on, right? So it's really a rotating blob, and the turbulence is really strong. It's basically the injection scale of turbulence. For those who are experts in turbulence, the injection scale of turbulence is basically a few kiloparsec. Right? In the Milky Way, the injection scale of turbulence is more like 100 parsec. So it's really a thin disk. Here, this is 10 times, 20 times larger. Right? And we're talking about the dwarf galaxy, right? Which is way, way, way smaller than the Milky Way. So, it's really a completely different regime. It's really the feedback-dominated regime. And so these were more like the first simulation we were doing like 10 years ago, trying to amplify the field. And indeed, so if you look at the magnetic energy, indeed, so this is the no feedback case on the left, you do amplify the field. You do, right? But it's not a dynamo. I want to make this point very clear, right? Why is it not a dynamo? Because the magnetic energy is growing as a function of time linearly, actually like the square of the time, t to the second power, right? And that's this dark line that you see, right? This solid line. And these are different resolution, right? So you have different resolution, and you see that we always get the same result, which is a weak amplification. If now you inject supernova feedback in the game, then you have a very turbulent galaxy. Then you see that there is a completely qualitative change here, which is that now we have an exponential growth. Okay, the growth is now exponential. It's not linear here, it's exponential. And you see that we have straight lines in this log lean kind of diagrams. You have straight lines, which means you have exponential growth. And the other sign that we have a dynamo now is that the growth rate depends on the resolution. So the higher the resolution, the faster the growth. And why is that? It's a well-known mechanism. It's because the underlying mechanism for the dynamo is based on vortices. You have small vortices in the turbulent flow, and you take a feed line, a feed loop, you stretch it because of the shear motion in the turbulence. Then you twist it because of helical motion, we call them, and then you fold back in. And then you need magnetic dissipation, you need magnetic reconnection to go back to a single loop like before, except there is now twice the magnetic energy. So you see that's the mechanism when you have a turbulent flow to create a dynamo. But the key point here, and I want to make this clear, is that in order to get this stretch, stretch, twist, and fold mechanism, you need to resolve the vortices. And in order to see some helical or vertical motion in the flow, you need at least 2 cells across the vortex, right? Otherwise, you don't resolve this motion, right? You need a velocity here, right? So you need 2 cells across one vortex. You need enough resolution to resolve those motions, right? And actually, that's why the better the resolution, the smaller the vortices you can resolve, and the smaller the vortices, the faster the growth rate, the faster the twist takes place, right? And so there is a critical resolution. If you fall below a critical resolution, which in our case was 40 parsec, so you see that's a very weak dynamo. It's almost flat, right? It is an exponential growth, but it's very flat. Okay, and those are well-known facts from the dynamo theory, that you need a critical resolution, or in the jargon, you need a critical Reynolds number, in order to see the exponential growth. The other thing that we know is that this growth will not go all the way to infinity. It will saturate to roughly 10% of the turbulent kinetic energy. So if you have a very turbulent flow with a lot of kinetic energy in turbulence, the magnetic field will saturate at a higher value. If you have a weaker turbulence, the same mechanism will occur, right? But the saturation will be at smaller magnetic field value. And then, then remember what we found in the observations: high redshift galaxies have a higher field than low redshift galaxies. In this picture, it works like a charm, right? Because high redshift galaxies are also more turbulent than the present-day galaxy. Okay, so this is the typical signature of the turbulent or small-scale dynamo, depending on what terminology you prefer to use here. Okay, I'm going to skip that. Okay, so now I want to show you this, which is a very brave attempt we did 3-4 years ago with a student to try now to obtain this small-scale dynamo in a dwarf galaxy at high redshift. So to do this with the Sphinx project, we couldn't do it. We need to have, as you have seen before, right? We need to have at least 20 parsec resolution. That's the critical resolution in order to see the dynamo in the dwarf galaxy. And indeed, in this cosmological simulation, so the white circle is the dark matter halo, we do form, you see the density is very messy, right? It's turbulent, and we do form turbulence-dominated dwarf galaxy. And we do see, so this is the magnetic energy in the box as a function of age, we do see a weak, slow turbulent dynamo. And it's consistent with what we have seen in the isolated case, in the idealized isolated case. That's 20 parsec give you a weak-ish dynamo. So here you see it's an exponential growth. It's a clear exponential growth, but it's very slow, right? And so it's wrong, right? It's too slow. Okay, so we're never going to be able to amplify the fields to 10⁻⁶ Gauss at this rate. So okay, so the situation here is that we are demonstrating that there is a weak dynamo occurring in those conditions in dwarf galaxies. But we are also demonstrating that the resolution you need in order to get fast enough results so that you reach the saturation quickly, not as fast as the nature, infinite resolution, it's really fast. But for us, we can reach the saturation, not too slow, let's say, and have a realistic prediction. Right? That's too difficult, at least for this kind of simulation. So then we need to use what we call a subgrid model. Okay, so that's the trick we used to be able to model now giant Milky-Way-like galaxies. We use a subgrid model. Okay, so subgrid models are used in engineering a lot to describe turbulent flows around planes and turbines, stuff like that. And these models have been developed by engineers and physicists for decades. And they are basically, the idea is to come up, instead of using the ideal MHD equation, we use the ideal MHD equation, but for the mean flow. And we treat the perturbations, the random fluctuations with respect to the mean flow as a separate entity. So you basically divide the scales into small scales, which are unresolved scales, which are smaller than the computational cells, and resolved scales that you can compute with the computer, which is usually called the mean flow. Right? So you have the mean flow and the perturbation with respect to the mean. And so you can derive mean flow equations by doing this scale separation. And here I'm showing you the equation that describes the kinetic energy of the unresolved turbulence. the turbulent that is inside our computational cells. And of course, there is a lot of modeling involved. If you're interested, I can give you all the details. But the key point is that you have a creation term, which is usually due to shear, which is usually modeled through shear, where now U is the mean flow velocity. Right? And then there's a destruction term of turbulence, which is also called the dissipation term, that we model by this simple exponential decay. And what are those parameters that we plug in? Those are the mean field equation parameters, and they are usually also referred to as the mixing length theory, where L, the length, is the parameter, and here we take the length equal to the grid size. And so you see that if you converge to 0 grid size, then this subgrid model disappears. If your flow is very turbulent, then this subgrid model just prolongs the turbulent model from the result scales to the unresolved scales below the grid scale. Okay? And so this new equation that we solve, we have an additional equation, allows us to estimate the velocity dispersion of the turbulence inside our computational cells. Okay, that's the trick. So we use it for star formation too, but I'm not going to discuss this here. If you're interested, come talk to me later. Okay, so now that we have this velocity dispersion of turbulence, now we can also derive a mean field equation for the magnetic field. Right? So we write B as B, which is the mean field, plus B prime, which is the fluctuation. And you can rewrite the induction equation in this case with two terms. One term, which is the mean field induction equation, the one we solved in the code already, and a new term, which is due to the fluctuation. And this is the turbulent non-ideal term. So we had the Biermann term before, remember? Now we have a turbulent term in the induction equation. And now the whole game, of course, is how do you model this turbulent electric field? And so we need a closure model. And so in what we have done here, a lot of caveats here, of course, we use the so-called alpha closure model, where we multiply the mean field B by an alpha tensor. Right? And we took this tensor to be proportional to identity matrix. And the level of the turbulence, sigma t, is used to normalize this tensor. So that's how we amplify the field linearly. And this basically tells us that the unresolved eddies that we have inside our computational cell are driving the dynamo at a speed which is given by the speed of the largest eddies in our unresolved scale-separated flow. Okay, so that's the first ingredient, the growth of the subgrid model. The second ingredient is that we have to saturate, of course, this dynamo. We have to stop the dynamo once it reached a fraction of the turbulent energy. And here we were conservative. We used a small fraction, but of course, the value you choose here, 0.1%, is a parameter of the model. Right? And 0.1% is very small. We can use more. If you use less, then it doesn't work anymore. Right? So we have to use it at least 0.1%. But remember, the theory of the turbulent dynamo tells you that it's more like 10%. Right? So 1.1%, we're very conservative. But it's still a caveat, right? It's not. Okay, so now once we do that, then we can rerun the Milky-Way galaxy formation simulation I showed you at the very beginning. But now with magnetic field and with this subgrid dynamo. And this subgrid dynamo basically bypass this crazy resolution requirement we had before. So now we are good, right? We just augment our model by all these unresolved scales that we need to get the dynamo. So now I will show you a few results here. This is work in progress. I mean, the paper is in preparation. So you see the Milky Way at redshift 4, the Milky Way progenitor at redshift 4. You see the surface density here on the left, and you see the magnetic field on the right. And the white circle is the virial radius. It's quite strong, right? So we have magnetic fields of the order of the micro-Gauss, but outside the galaxy. The galaxy is really high magnetic field here. It's more like 100 micro-Gauss. We have a very strong magnetic field in the galaxy, very strong magnetic field in the halo. If we move to low redshift now we have this nice quiescent disk, right, that I showed before. So this is the disk zoomed in, this is the halo, so this is the entire halo you see on the right panel. And the magnetic field now are much weaker. So now we are more like nano-Gauss or 10 nano-Gauss level in the halo. And inside the disk, it's 10 micro-Gauss. So it's weaker, right? And that's consistent with the fact that turbulence is weaker. So we also computed Faraday rotation maps to compare the observations. So Faraday rotation is basically when you have a quasar line of sight, the polarization of the light rotates through the magnetic field. And you can predict what will be the signal here. And so I'm going to skip here. We compared high redshift observations to actual observations performed by my colleagues in Zurich. And you see that, so this is what we see in cyan, that's our simulation. And the gray band is what they are observing in these distant quasars. So it's not completely off. I would say we are a bit weak. We are a bit weak yet, but we are close to the correct value. So this is a great, kind of game to play to calibrate the model at redshift indices 4, very high redshift, and also by looking at Faraday rotations in the Milky Way today, we can also compare to the nearby galaxies. So there's a lot of stuff to do here once we have this model, which is now, I would say, relatively self-consistent. So let me summarize my talk. So seed fields at high redshift are generated through this Biermann battery process. And by high redshift, I mean between redshift 10 and 6. And it's actually surprisingly complicated. Right? You have the linear regime, the photonization regime, and then the galactic outflow regime. And then while galaxies are forming, you slowly transition into the turbulent dynamo. And so the turbulent dynamo really amplify the field really efficiently inside the turbulent ISM. And then, of course, the strong galactic outflows will push this field back into the IGM. I didn't really mention this too much by lack of time. But so the IGM will be populated by a much stronger field than this tiny 10 to minus 20 Gauss field through the galactic outflows. Right? And the question is, how much of the IGM can you pollute with this magnetic field? Do you have some pristine 10 to minus 20 Gauss regions, or is the universe full of nano Gauss magnetic field? Right? That's the big question. Right? Today, we are more in the quiescent disk regime, where the turbulent dynamo is much weaker. And that's actually where large-scale dynamos can help maintaining the field to a high value. Right? And so large-scale dynamo are not dead by far. They are very important to explain what's happening in the quiescent disk regime and maybe maintain the field. Otherwise, because the turbulence is so small, the field can decay. Right? So that's another open question, right? How the large-scale dynamos are taking over the turbulent dynamo at high redshift to maintain the field. One key point I want to make is that to solve this turbulent dynamo, you need a hell of a resolution. It's really challenging because of these small eddies you need to resolve, especially if you want the dynamo to be fast. And we kind of gave up on that for the galaxy, the giant galaxies, and we used instead a subgrid model that seems to be doing the job, of course, with some caveats. That's it. Thank you very much.
Well, I see already a question, so please.
Yeah, you referred to this a couple of times, magnetic field decay. So I just wanted to ask about this. So you pumped up this turbulent galaxy with winds, with magnetic fields, and they bubbled up. Why do you have to keep generating them in the disk? What's the time scale and the mechanism for the fields decaying there?
So the field, if you don't pump up kinetic energy constantly, the field indeed will decay, and the decay is governed by numerical diffusion in our case. In nature, it's governed by dissipation process at tiny scale. Right? So the decay is usually slow. Even in our case, where we have a lot of dissipation, it is slow. Right? So now you need to pump in kinetic energy constantly, and this is done through star formation. So it's true that if your galaxy, for some reason, stop forming stars, then the ISM will become very quiet, and the dynamo might shut down. In this picture, you need a source of turbulence, and this source of turbulence is supernova explosions in the ISM driving the turbulence. Now, the origin of turbulence in the ISM is another story, right? Because you have also rotating flows, gravitational instability. All these processes are not related to supernova explosions, but they can also drive turbulence. But in this picture, it's mostly supernova explosion. So if you don't have star formation anymore, if for some reason your galaxy shut off, then probably the dynamo will decay, unless it's maintained by some large-scale dynamo process.
Yes, but the fields themselves will not decay on the same time scale. The dynamo will stop amplifying them, but they will still be there, right?
They will still be there, but they will decay they will reconnect slowly, and they will decay at the dissipation scale, which is slow. I agree with you. It's very slow, right? It's a slow process.
We had a question, Xiao on Zoom, so maybe we can try.
So I wonder, so you talk about the evolution of the field strength. So I wonder how the correlation length of magnetic field evolves at low redshift and high redshift.
It's a very good question. The work I would like to quote here is the work by Naos and Narayan, who worked out the linear regime, and they computed the mean magnetic field, but they also computed the magnetic field power spectrum through this theory. And you can see that it peaks at a specific scale, which again is due to this very detailed thermal history and very subtle thermal history in the, I would say, pre-ionization universe. And there, in the linear regime, you can predict very nicely and very accurately the correlation of the magnetic field. Now, if you look at the nonlinear regime that we have described today, then the picture is complicated, because now you have to enter two length scales. One is the typical Strömgren sphere that will imprint on the magnetic field at given length scales, so the Strömgren sphere radius. And then the other length scale is the galactic outflow, which seems at redshift 6 to be at smaller length scales. And so I don't have an answer for you, but I would, that's exactly, actually it's a student project I proposed recently, to compute the correlation function of the field at redshift 6, once ionization and the very first generation of dwarf galaxies are formed, what will be the correlation function? So I can point you to the Naos and Narayan paper for the linear regime. For the nonlinear regime, I don't know.
Thank you.
So we had, in order, I see the Roman had a question.
Well, I had a very similar question, maybe following up to a later epoch when you have when you argued quite persuasively that field amplification can be done by this turbulent dynamo, and the smaller scales you are looking at, the faster it goes. And to me, this would suggest that you also would have a very small scale dynamo, a very small scale magnetic field. So you're always showing, the maps of B squared and so on. But your Faraday rotation data, for example, fell significantly below, which to me suggests that presumably the scale of this magnetic field is actually very small, not even this, probably inconsistent with what we are observing in the galaxies around us.
No, it's a very good question, so there is two answers. The first answer is that, let me try to go back. The first answer is that dwarf galaxies, the scale at which you inject the turbulence in dwarf galaxies is very large, actually. It's the size of the galaxy itself, meaning that you expect, at least in this turbulent-driven scenario, an injection scale which corresponds to the largest scale you can have in this turbulent dynamo picture. The injection scale is quite large. It's 1 kpc, 2 kpc. If you move to larger galaxies and they are still in the turbulent mode, you can even go to higher scales, right? On the other end, if now you move to the quiescent regime, like the panel on the left, you have a very thin disk, the injection scale is tiny. It's true, today in the Milky Way, the injection scale is tiny, right? But my claim here is that the large-scale field that you see can be due to a large-scale dynamo. We haven't discussed this today, right? But can be also the remnant of the large-scale injection, the large injection scale we had when the galaxy was feedback dominated. And then once you have this large-scale pumping with very large eddies, then once you move into a quiescent regime, you just squeeze that back into a thin disk, and you get your large-scale.
But this is not captured in the simulations.
This is captured.
Okay.
Yeah, so I didn't have time, but this, you see, this is an experiment we did, very simple experiment, where we did this dwarf galaxy. So you see it's a mess, especially the edge-on view. You see the edge-on view on the lower left panel. It's very turbulent. I mean, you have like a kpc thick disk. And then we shut of supernova explosions. So of course the disk was maintained like a turbulent state, just collapsed to a thin disk, right? And that's what you get. Right? So you see the lower left panel is very thin, very thick, boom, very thin. Right? And all this turbulent field that we had in the galactic outflow is now squeezed back into a thin disk. And we do see, and that's the magnetic field here, that's a resulting magnetic field. You do see large scale field, which are the relics, the remnant of the large scale field you had in this turbulent large scale bubble. Well, this is for dwarf galaxy. Now, if you move to a Milky-Way-like galaxy, it's another picture. We have to be more careful. And all these, by the way, all these subtle geometry that we see here, if you move to the subgrid model, we completely lose them, right? So that's another caveat of the subgrid model, is that we lose all these subtle aspects.
Thanks. Well, there was one Bin on Zoom.
Oh, hi. I want to ask about so you mentioned the RM, the rotation measure that you're generating disagrees. It's too low compared to quasar measurements. So what kind of thoughts do you have on how to increase this RM by a few orders of magnitude? Let's say increase your saturation level from 0.1% all the way to 10%, or you do dissipations slightly slower, or you include some additional feedback on KPC on a larger scale, additional, let's say, Fermi bubble like wind or anything. What kind of thoughts do you have to increase this? So
actually, what we have shown is that if you increase the saturation parameter, if you increase it, it doesn't change the results, because from where we stop the saturation of the subgrid model to the field we see, which is actually much larger than the saturation, it's actually mediated by the resolved motion. So if you increase the saturation parameter, it doesn't change the result. If you decrease it, it changes. The field becomes too big. Right? So I think we put it at the smallest value where it kind of does the job, and then if you increase it more, it doesn't really change the result.
I see.
The problem with this plot is that we need to make sure we're comparing apples to apples. And the problem is that those high redshift observations, we don't really know what are the halo masses that this quasar line of sight is intersecting. And of course, if you have different halo masses, you may have different level of turbulence, different outflow strength and sizes, and this might change the prediction. Here we only have one halo, which is the one you see in the upper one. And we have one halo profile, right? In the observations, you're intersecting many different halos of many different masses and turbulent state. And so that would require a more cleaner statistical comparison to really conclude whether we are missing something from the physics, or whether it's just an observational bias because you're intersecting different halo sizes.
Yes. Yeah, I would guess that FRBs with this RM measurement with fast radio bursts would help in constraining the halo RM profile. Thanks.
Another question.
I'm a bit surprised by the construction of the subgrid dynamo. There is, as far as I could see, there are only linear terms based on the mean field that enter here, while the effect of the subgrid is clearly going from one exponential to a steeper exponential. Right? You showed that before in the isolated case.
Oh,
exactly this one, yeah. So what am I missing, right? How can you close the subgrid if it becomes basically a steeper exponential if the only thing you have available are linear order correction terms?
So here, what this plot shows is that the more resolution you have, the faster the growth. Of course, I think it's connecting to the other question we had before. It's very important you measure at what scale this happens. Right? And I didn't have time to show power spectra, right? But usually the larger the scales, the smaller the growth at that scale. Right? So of course here it's the total magnetic energy in the the system, and it's dominated by the small scales. That's why you see something very fast, right? But now if you compute the magnetic energy only at the largest scale, then this will always be the same. This will converge, right? And this will be slow, of course, right? So in the subgrid model we use here, the growth rate we obtain is the growth rate at the grid scale, which is the largest scale of the unresolved turbulent cascade. And this, of course, depends on the resolution. Right? And so it's true that if you go back to this modeling here, you see that this parameter L, we choose it to be delta X. Right? And so if delta X is reduced, the growth rate that we will obtain here will depend on the resolution, right? And will become faster and faster. Right? So we cannot get the right behavior. Right? We always measure the growth rate at the scale of the cell, right? And this kind of works out. Some caveats, right? I want to stress that the main caveat here is the scalar nature. I mean, the tensor here is proportional to a density, and that's not what turbulent dynamo theories are predicting at all, right? So I want to stress that this is just a Purzman version, try to put the magnetic field to a value which is low, so that with our not so good resolution, the code can take over from there and then do the large-scale motions. Right? There is a lot of improvement to do here on this alpha tensor. Right? But I'm not sure it's the point here, really.
I see the Sukanya, the question from Zoom, so maybe if she still wants to ask. Maybe she didn't hear me. There is another question from Zoom from Lachlan. You mentioned that turbulent amplification gets you 10% of the way to equipartition. Can you comment on what gets you the rest of the way to equipartition?
Yes, very good question. I didn't have time to explain too much, but so you see here a diagram here. Let's focus on the redshift 0 diagram. Okay? So this is the magnetic pressure as a function of the gas density in our halo, in our Milky-Way size halo. And the upper dashed line is obtained assuming that the field goes as rho to the 2/3, or the magnetic pressure goes as rho to the 4/3, which is the ideal image prediction. Right? And the red cross, which is used as a normalization here, is actually assuming that the field is in equipartition with the turbulence. Okay, so the magnetic energy is indeed in equipartition. And remember that I told you that the subgrid model will take you to 0.1% of equipartition. So what can bring you from there to equipartition? And actually, these are the resolved motions. So the resolved motion, so we do have some resolved turbulence, not at the sufficient resolution, but these resolved turbulence will amplify the field a bit more. We have also the rotation of the disk. The rotation of the disk will also bring you an additional amplification. It's not exponential, right? It's a linear amplification, but it still pumps the magnetic energy to a higher level. And all these combined, you reach equipartition. So that's why this subgrid model is actually doing a little bit at the beginning, and then it disappears. And then the simulation does the rest. Right? And the rest is to bring you to equipartition.
Okay. So I see that there are still questions on Zoom. So for me, we could still go on. I don't know how much time, how this works. So yes.
Let's do the last two questions.
Okay, let's do the last two questions. And let me also remind that Professor Teyssier will be here at the AES for the whole afternoon in Bloomberg Hall. And there are still open slots if you want to go talk to him. So you can take that option as well. So yes, let's take the last two questions. I see from Zoom there was Amitava first.
Thank you. Very nice talk, Romain. Just following up on your closure model for the dynamo, and I just wanted to ask you, you said that this is a work in progress, but as you know, at the level of fluctuations that you actually have in your simulations, alpha T by itself has strong quenching corrections. This, of course, depends very much on how much helicity you have in the problem and so on and so forth. When you are making assumptions regarding what types of alpha T, you've also thrown out other important things that you know about, such as the beta effect and what kind of structure it has. How sensitive is your result to exactly what you do for alpha T? And it would be good to have a self-consistency check that at the level of fluctuations that you're talking about, the model for alpha T that you actually used is consistent with the level of fluctuation or the back reaction that might occur away from the kinematic results. These are not easy questions, but I wonder how one would know that one has the right dynamo in your problem.
Yeah, so the quenching, so you mentioned the quenching of alpha T. So
right.
The way we approached this problem was to really have a simple model where once we reach 0.1% of the partition, we set alpha to 0. And so we indeed have an alpha T formula, which is when the magnetic energy is very, very weak, it's basically sigma T. And then we have a mathematical form that transition your sigma T asymptotic value to 0. And this form that we used is a very simple form that was proposed, for example, in the Brandenburg review, to model the approach of saturation. And so we didn't go much further than that.
Does that have an RM dependency? RM, your magnetic Reynolds number dependency. The form that you took, does it have an RM dependency?
Yeah, you're perfectly right. There is a dependency on the dissipation mechanism. You're right. The Reynolds number and also the Prandtl number, which is how the magnetic dissipation compares to the viscosity. And you're right. There is a lot of inputs that need to be added in this model to make it more precise. But here I think we are not there yet at this level of, I would say, accuracy. But that's clearly those paths that we would like to explore in the future to make the whole closure model more realistic.
Thank you.
Okay, so there is still a question by Matthew, and let's make it this last because there is a lunch after that. So please, Matthew from Zoom.
Yeah, thank you. I'll try to keep it short. Nice talk, Ron. I'm really excited to talk to you about this in person. Sorry I couldn't be there. So I had two questions which were somewhat entwined. So you focused more on the galactic fields, and I was curious about your thoughts on intercluster fields, whether based on other simulations you had done in a more cosmological environment, whether you see that these fields are spewed out from the galaxies, or whether they're grown up in situ from the ICM turbulence in the simulations. And one thing that connects to this that I'm curious about connects to an earlier point that you made, where you increase the resolution and the dynamo is faster because the eddies turn over faster. If you just take Coulomb collisions for the ICM, the Reynolds number is order 1. The gas Reynolds number is 1 to 10 or something like that. So there's I guess I'm just bringing that up in the context of how does one know what to do with the subgrid model in terms of the Reynolds number in the different environments? Because it could be different inside the galaxy versus in the ICM. Thank you. Just thank you.
So quick answer. The subgrid model that we use is only restricted to what we call in the simulation the ISM, because we want to restrict this model to dense gas supersonic turbulence, which is what we have once the density is higher than basically the star formation threshold, the ISM threshold we adopt in our simulations. So in the ICM, in the intracluster medium or in the IGM even, the only source of magnetic energy we have is either the Biermann battery fields or the fields that are transported by the outflows, the galactic outflows. And we don't have any subgrid dynamo out there. So the only mechanism we have are transport of the field from deep inside the galaxy to the IGM and the ICM if we make big cluster simulations. In this model, we don't have any, I would say, subgrid model to describe the magnetic field in the ICM. So in the, we haven't done that yet, or I have not done that yet, but if we move into galaxy cluster simulations, I guess what we would see is a bunch of galaxies forming stars, injecting metals and magnetic fields in the ICM through these galactic winds, or through gas tripping and such. And all the magnetic field that we will see in the ICM will come from that in this model. And it will be interesting to see what will be the prediction of the magnetic field in the ICM, whether we need some extra dynamo because maybe we're going to obtain something way too weak. What we can say now is that this preliminary simulation we did, the magnetic field we see in the galactic halo, which is this region around the disk here, seems to be at the actually 10 to 100 nanogauss level. So it's 10 nanogauss level, which seems to be okay for Milky-Way-like objects. But this is not ICM yet, so I cannot say about the ICM. But in this picture, the ICM magnetic field will take its origin from the galactic outflow.
Great, thank you.
Okay, so let's thank Teyssier again. And